Model optimization is one of the toughest challenges in the implementation of machine learning solutions. Entire branches of machine learning and deep learning theory have been dedicated to the optimization of models. Hyperparameter optimization in machine learning intends to find the hyperparameter of a given machine learning algorithm that deliver the best performance as measured on a validation set. Hyperparameters, in contrast to model parameters, are set by the machine learning engineer before training. The number of trees in a random forest is a hyperparameter, while the weights in a neural network are model parameters learned during training. I like to think of hyperparameters as the model settings to be used so that the model can optimally solve the machine learning problem. Some examples of model hyperparameters include the learning rate for training a neural network, the C and gamma hyperparameters for support vector machines, the K in K nearest neighbors. Hyperparameter optimization finds a combination of hyperparameters that returns an optimal model which reduces a predefined loss function and in turn increases the accuracy on given independent data. Hyperparameter optimization methods. Hyperparameters can have different, sorry, hyperparameters can have a direct impact on the training of machine learning algorithms. Thus, to achieve maximal performance, it is important to understand how to optimize them. Here are some common strategies for optimizing hyperparameters. Manual hyperparameter tuning. Traditionally, hyperparameters were tuned manually by trial and error. This is still commonly done, and experienced engineers can guess parameter values that will deliver very high accuracy for ML models. However, there is a continual search for better, faster, and more automatic methods to optimize hyperparameters. Grid search. Grid search is arguably the most basic hyperparameter tuning method. With this technique, we simply build a model for each possible combination of all the hyperparameter values provided, evaluating each model and selecting the architecture which produces the best results. Random search. Often some of the hyperparameters matter much more than others. Performing random search rather than grid search allows much more precise discovery of good values for the important ones. Random search sets up a grid of hyperparameter values and selects random combinations to train the model and score. This allows you to explicitly control the number of parameter combinations that are attempted. The number of search iteration is set based on time or resources. Scikit-learn offers the randomized search CV function for this process. Bayesian optimization. The previous two methods performed individual experiments building model and with various hyperparameter values and recording the model performance for each. Because each experiment was performed in isolation, so it's very easy to parallelize this process. However, because each experiment was performed in isolation, we are not able to use the information from one experiment to improve the next experiment. Bayesian optimization belongs to a class of sequential model-based optimization algorithms that allow for one to use the results of our previous iteration to improve our sampling methods of the next experiment. Gradient-based optimization. It is specially used in the case of neural networks. It computes the gradient with respect to hyperparameters and optimizes them using gradient descent algorithm. The calculation of the gradient is the least of problems, at least in times of advanced automatic differentiation software. And while there are lots of people who used to use this kind of idea, they only did this for some specific and well formulated problem, example SVM tuning. Furthermore, there probably were a lot of assumptions. Next is evolutionary optimization. Evolutionary optimization follows a process inspired by the biological concept of evolution, and since natural evolution is a dynamic process in a changing environment, they are also well suited to dynamic optimization problems. Evolutionary algorithms are often used to find good approximate solutions that cannot be easily solved by other techniques. Optimization problems often don't have an exact solution as it may be too time consuming and computationally intensive to find an optimal solution. However, evolutionary algorithms are ideal in such situations as they can be used to find a near optimal solution which is often sufficient. One advantage of evolutionary algorithm is that they develop solutions free of any human misconceptions or biases, which means they can produce surprising ideas which we might never generate ourselves.